this is the gel that we made up last session. All it literally is we've put this tape on, poured it in to prevent it from overflowing, and then let it set. So as you can see, it's actually quite gelatinous right now. It's quite hard. And what we use this comb to in here while it was setting to make these wells. And these little wells in here is where we're going to put in the different DNA fragments with the different restriction enzymes. So basically what happens is, because of the negative charge of the phosphates in the DNA molecules, it will, depending on the size of it, it will move further along the gel. So obviously the larger the molecule, it won't go as far along the gel. So if we pop it in here, if you see these two electrodes, this one is negatively charged, this one's positively charged. So as the phosphate is negatively charged, it will move towards the positive electrode. So that's why I put it this way around with the wells on this side of the gel. Pop this on. Once this is plugged in, it will run a current that will go in that direction.
First thing first is you've got to use one of the tip things that are in here, this lot. You just sort of use the pipette, you stick it right in, you have to make it really firm, just so it sticks on. There you go. Right. When you're pipetting stuff, what you need to do is take the sample with the liquid in it, in this case it's just water, and then dip the pipette in and then press down. You'll feel a resistance. At that point you leave it in there and then pull back up again, and you should get a tiny bit, and maybe you can see it, really tiny bit of liquid in there. And then you take that over to the next vial, and what you do is drop it down, and this time you feel the resistance and you go further. You push it down past the resistance and out again, and then you'll have got the liquid just in there. Don't know if you can see that either.
How much have you just delivered?
That was 5 microliters.
5 microliters?
Yeah, just a tiny bit. And then when you're getting rid of the pipette, you always change the tip between each sample. So what you do is just take the pipette up.
Well,
correct. That's incorrect, actually. That is incorrect. That is how not to do it.
Okay.
This is how you're meant to do it.
This is how you're meant to take the tip off the pipette. It's just there's the second button here. That's the one that gets all the resistance. That's the one that takes the tip off. So you just do that. Pulls right off. And you stick that in a bin.
Okay, so here's the tube with the sample in it. Okay. This one. So I'm just going to close the lid of it and put it into the centrifuge. So it has to be balanced by the other one in the opposite position. And then I'm going to close it and pulse it for a few seconds. Okay, that should be okay. And then open it. And yeah. So the sample will have gone to the bottom of the tube. So you can see that.
okay.
Yeah.
I don't think I can't do that one. Just to the right one. Right. Hello.
Seems really right. What tubes do we need?
How much do you need? Money for the money
This will be mixture.
We have 3 tubes here, using a different restriction enzyme known as SAL1 E12B in a mixture of both. Here you have an output of pipetting 10 microliters of one into the other. And
That's 1 litre.
yeah, basically.
All 3 have 10 microliters of plasmid, which is PJX6P1. So a kilo-based ladder is essentially a calibrated scale for when we do the gel electrophoresis. So basically, there are 5 known fragment sizes in this case, which is 1 kilobase, 2 kilobases, 3 kilobases, 4 kilobases, and 5 kilobases. So essentially, then when we get the centrifuge of the plasmid, then we can compare the placement of the plasmid to the ladder. So then we can estimate its size. So we know how many kilobases the fragment.
Just adding SAL1. So now I'm going to do the mixture.
You could go right on top of it like this. Like that. Oh, that's good. That's good. That's good. Good.
And then finally just the DNA by itself. It's going to put the electrodes on. And then you should start to see bubbles rising.
Okay, we're just going to take the lid off this, stop the current, and have a look at how the gels run down here. You can just about see the banding patterns, how the dyes move forward in the gel. But to get a better look, we'll need to stain it properly. Okay, we come. I was just doing a final shot of what it looks like in the gel there on close up. Okay.
Sticking my finger.
We'll look at the gels at the end. You will have digested fragments according to your predictions, and you need to know which well you put which sample in. Otherwise it's just going to look like, what does all this mean? If it works well and the ladder is there and Eco R5 is going to come, what is your prediction for Eco R5? Anyone?
A single fragment of 5 kilobases.
Only cuts at one point.
Because it only has one site which
Recognition
cuts,
type.
So it's got one restriction site.
which will split and open the plasmid.
like a
but also
circle.
one
It's
fragment.
just going to open the plasmid
At one point.
at one point, so you're going to get one
Whole
band.
length.
It's going to be,
10 or the largest.
you reckon it's
Yeah,
going to be
you'll
about
move the
10?
needs.
So
No, because
It depends how big
It
the
depends
plasma
how
Oh, it's
big
is.
5
the
kilobases.
yeah.
5, so.
really the scale should have
So
been
it should be-
before.
Just redo the scale.
It should be near the bottom.
The scales a bit.
Sorry, it doesn't matter.
Oh,
So everything's
It's not-
relative.
The scale isn't necessarily linear.
True.
Okay, so there are different factors at play because
Yeah, with it.
with DNA, if you've got a buffer solution in which is making it all negative, the longer the DNA fragment, what does that do to the charge?
Increases it.
Sorry,
Increases
it increases the negative charge.
More
What's
positive.
that going to do to the pulling effect in the magnetic field in the electrons?
Great.
It's going to increase. So there's going to be a greater draw and a bigger DNA from the electromagnetic effect, but because
It's also
physically it's a lot bigger, it's got to plough its way through gel more, it's going to slow it down. And the dominant factor is the size over the charge, but that's why it's not necessarily it's not a linear relationship, so you can't necessarily say it's equal spaces between the ladder. Okay, so we reckon we might have a restriction fragment of about 5 kilobases with Eco RV. What about the next lane?
Cell 1.
Cell 1.
That also cuts at one point, so depending on the size of plasmid, it would depend, but it should also be something near to plasmid. It should be
So
very
It'll
near.
be exactly the same.
It should be, if it's only one restriction site
Yeah,
there.
but it should be the same.
Should be the same.
Now, next point,
It's gonna, it might
Mixture is the interesting one.
mixture.
Done.
What's going to happen?
You're going to have two. One's about 1 kilobyte, the other one's about 3 kilobytes.
Right, you're going to point that on path then to explain why.
Doesn't add up.
I just come
Put it on a desk.
I'll just come from them.
Yeah. Is it recording?
Yeah.
Okay, say this is the plasmid we're working with. the SAL1 restriction site is here, and the eco-RV is here, and the whole thing's about 5 kilobyte bases. So from here to here is 1 kilobase, and from here all the way around to here is 4 kilobases. So from here to here must be 3 kilobases. Therefore, as it cuts here and here, we'll see one that's 3 kilobases, and the other one would be this distance to that distance. Will actually be 2 kilobases. Basically that one plus whatever's left over, which is another one, essentially. So we'll see one at 3, which is about here, and one at 2, which is even higher, which is what we predict.
What are we looking at here?
Ladder.
So what are these points here?
Calibration.
The calibrating ladder. So
Represents the magnitude and size of different bases.
the size. Okay, and what are these bits here?
The two different sizes of the plasmid which have been cut out by the restriction endonuclease. So 2 and 3 kilobases.
Alex and Henrik hiding behind it. So that's kind of Sam.